All right, so this problem says a single force Fx equal to minus 4x. And let me remind you, you guys remember the force that a spring exerts on a mass? This is Hooke's law, it's like that. So this is exactly that, and there is the spring constant, okay? So acts on a 1 kg body. When x equal to 3.5 meters, the speed of the body is 4 meters per second. So when this is stretched 3.5 meters, 3.5 meters is roughly the width of this table. Okay. So that's this is a very weak spring, and it's been stretched quite a bit. The speed of the body is 4 meters per second. What is its speed at x equal to 2 meters? Okay, so this problem uses a couple of things. You guys saw the work energy theorem. The net work done, that is the work done by all the forces acting on the object, shows up as change in kinetic energy of the object. Okay, so in this problem, this is the only force acting on the object. Okay? And the work done by this force is this integral. Okay? And that shows up as the change in kinetic energy of the object. All right? So, and the initial position is, the initial velocity is that. The initial position is 3.5 meters. The final position is 2 meters. Okay? So 3.5 meters, 2 meters, minus 4x dx equal to 1/2 m v final square minus v initial square is 4. All right, so the integral of x is x squared by 2. Okay, so this becomes minus 4x squared by 2, 3.5 to 2. And the mass of the object is 1 kg. Okay. So, all right. All right, so this is the final velocity is 6.1 meters per second. Okay, and this, let's make sure we understand this. Okay, so here's the equilibrium position. You stretched it 3.5 meters. It's going at 4 meters per second. It could actually be going that way or this way, but as it comes close to the equilibrium point, it's going faster. Okay, and the spring goes fastest, the mass goes fastest at the equilibrium point at x equal to 0. Yep.
Did you just drop the square from the 4 on purpose? Or was that a mistake?
All right. So okay. So everybody understand that? So when you attach a mass to a spring and it oscillates, the mass is going the fastest there. It has the maximum kinetic energy there, and it has maximum potential energy when it's extended. And at every point, the sum of kinetic plus potential energy is constant. Okay, so let me show that to you. Okay, so this is a vertically oscillating spring. Okay. So this is oscillating vertically, so it has gravitational potential energy as well. Okay, so you see there's the gravitational potential energy, there's the spring potential energy, and there's kinetic energy. And we don't want any damping. Damping, what is damping? I'm sorry? Damping is friction. Okay. So right now we don't have any damping. All right. So here's a good illustration. So let's say this is your, since now this is bike week, this is your wheel on your motorbike. You hit a pothole and your wheel is oscillating. And then after you come out of the pothole, the wheel is bouncing on the road. Do you want that? No. So how do you stop that? That's what the shock absorber is doing. Okay, so you build in damping into your structures. Okay, if your bridge starts oscillating because of the wind, you build in damping to kill oscillations. Okay. All right. So damping is friction. Okay. In all big structures, you have that. The Burj Khalifa oscillates this much at the top. Yeah. You got to make sure that oscillations don't get out of hand. All right. But we'll come to damping in chapter 15. We'll talk about all of this in chapter 15. All right. So here's a 60 kg skier with an initial speed of 12 meters per second, goes up a 2.5 meter high rise as shown. 2.5 meters is roughly halfway to the ceiling. Okay. Find her final speed at the top, given that the coefficient of friction between her skis and the snow is 0.8. Okay. So this is one of the formulas you've seen. This is the work done by non-conservative forces. Okay. If you're pushing something, that's a non-conservative force. Friction is a non-conservative force. Okay. The work done by non-conservative force shows up as change in mechanical energy. Mechanical energy is All right, let me write mechanical energy. Mechanical energy is potential energy plus kinetic energy. Okay? So potential energy takes care of work done by all conservative forces. Okay. Is there a conservative force acting in this problem, in this situation? Very good. Very good, my friend. Okay. Okay, so the work done by friction force is gravitational potential energy plus kinetic energy final minus gravity initial. Okay. What we want to find is the final speed, so we want to find this guy. Okay. We know the height, so we know this guy. We'll take this to be 0, y equal to 0, so this guy is 0. Okay. So this guy is 0. So we know this, we know this, we need to find that. So let's calculate the work done by friction force. You guys understand that? All right. All right, so now let's put him on the slope. That's where he's being slowed down. That's where the friction is acting. Okay. And it's a kinetic friction force because it's moving. Okay. So here is his weight. This is mg cosine theta. And there's the normal force. The normal force is equal to mg cosine theta. So the friction force is mu k times Fn. Okay. And there is the friction force. And there is the distance. Do we know the distance that of the slope? Yeah. Yeah, you know it because you're given this angle and you're given this side. Sine 35 is this guy or that, so you can calculate that. Okay. So the hypotenuse is sine is, yeah. Okay. Okay. So the work done by friction force, the angle between the two is 180 degrees, and you know that friction force always, so cosine 180 is -1 friction force times the hypotenuse. Okay. So there's the work done by the friction force. And that is equal to, so the work done by friction force is equal to this. Okay? This is mgy final, kinetic energy final minus kinetic energy initial. Okay, so let me write this over here, minus mu k mg cosine 35 times h equal to mgy final minus 1/2 plus 1/2 mv final square minus 1/2 mv initial square. Okay, so that's the final potential energy, that's the final kinetic energy minus the initial kinetic energy. So what this is saying is the work done shows up as change in the mechanical energy. Okay. Notice something interesting. The mass cancels. What does that mean? So everybody, no matter who the skier is, as long as you're wearing the same skis, you'd have the same speed at the top. Okay? So mu k is 0.8, g is 9.8 meters per second square, 4.36 meters times cosine 35 should equal 9.8 times y final is 2.5 meters plus 1/2 v final square minus 1/2 v initial square. V initial is 12 meters per second. All right, so now let's calculate all of this. .9 meters per second. Okay. And let's make sure this makes sense. Okay, so you are going at 12 meters per second and you climb the hill and you're going at 6.9 meters per second at the top. And that makes sense. Okay, if there was no friction, would you be going faster or slower? Or at the same speed? I'm sorry? You'd be going faster. What did friction do? Friction, see this number was negative. This number is negative. What it does is it removes, if this was 0, this should equal that, okay? And now, since this is negative, you bring that to this side, that becomes a positive number, so this number has to be smaller, everything else being the same, okay? It's like you guys see this, if there's friction, what did friction do? It removed kinetic energy, it removed energy. Okay. So if there was no friction, then you would be going fast. A pogo stick has a spring with a spring constant of 2.5 times 10 to the 4 newtons per meter, which can be compressed 12 centimeters, that's about 5 inches. To what maximum height from the uncompressed spring can a child jump on the stick using only the energy in the spring? The child and the stick have a total mass of 40 kgs. Okay. So I'll do a simplified diagram. So here is the compressed pogo stick. And we want to know how high can the child jump. Okay. So in this situation, there are two forces acting, two conservative forces acting. The spring force and gravity is acting. Okay. And there are no non-conservative forces acting, so mechanical energy is conserved. Okay. Okay, so in the initial state, there's gravitational potential energy plus spring potential energy plus kinetic energy, initial, and that's equal to gravitational potential energy, spring potential energy plus kinetic energy in the final state. Okay, this guy is at rest in the initial condition, and when you're at the peak, you're at rest. So these two terms are zero. Okay. In this case, the spring is not stretched anymore, so the spring potential energy is zero. Okay. We'll take this as the reference level for gravitational potential energy. So that is zero. Okay. So what is this guy saying? The spring potential energies in the initial configuration got turned into gravitational potential energy in the final configuration. That's what happens. So you compress the spring, and that spring potential energy got turned into gravitational potential energy. Okay? Okay, so initials. Okay. So 1/2 kx squared okay, so that's how far you rose about the reference level, or about the initial position. Okay. And what is it that we are trying to find? What maximum height? So this is what we're trying to find. So y final is kx squared over 2mg. Okay, again, in this problems, this energy stored in the spring got converted to gravitational potential energy. Okay. And as it's rising up, it was moving faster, and when you first took off from the spring, you were going the fastest, and you slowed down and came to rest there. All right, so let's calculate this. The spring was compressed 12 centimeters, so that's that, which is 0.12 meters. 40 kg is the mass of the child, and this will work out in meters. All right, so here's a good habit to get into: take care of powers of 10. Okay, so what we'll do is, this is 10 to the 4. We'll make this 1.2 times 10 to the minus 1. That's squared 10 to the minus 2. So that kills 2 of those, and then one of them dies here. So that's 25. 25 into 1.2 squared divided by 8 into 9.8. Okay. So 45 centimeters. The child rises 1.5 feet. Okay. That was roughly Michael Jordan's vertical leap from standing still. So Michael Jordan had springs in his legs. So this says block 2 shows below slides along a frictionless table. So this is a frictionless table as block 1 falls. Both blocks are attached to a frictionless pulley. So this is frictionless, and they don't state it, but it's frictionless and massless. When it's frictionless and massless, what is it that they're trying to say? Do you guys remember? I'm sorry? No, what are they trying to say? What they're trying to say is the tension on either side and the string is the same. Okay? If this had a mass, then these tensions would be different. Okay? And you will deal with these kinds of problems at a senior level class. But for now, when this is massless, the tensions are the same. That's what they're trying to say. Okay, find the speed of the blocks after they have moved 2 meters. So this thing has fallen 2 meters, and they want you to assume that they start from rest and that the pulley has negligible mass. Okay. Okay, now, so this is an internal force. Okay, this tension is pulling on this guy in this direction. This guy is being pulled in this direction. Okay, and these guys are not doing any work. So I'll solve it 2 different ways. Okay, we'll use conservation of energy. Okay, so what is happening? Okay. So let's say if I drop this piece of chalk, what happened here? Very good. Okay. Potential energy was converted to kinetic energy. Okay, so when these guys fall, this guy loses potential energy. And where did the kinetic energy show up? In both these guys. Okay? All right. So we'll do it that way, and then I'll show you another way of doing it. Okay. So since only conservative forces acted, it falls 2 meters. Okay, so it fell from a height of 2 meters. Initial mechanical energy is equal to, okay, so, and initial energy is potential plus kinetic energy for the two objects. This guy's height doesn't change, so his potential energy remains constant, okay? And you can take different reference heights for two different objects. So for him, we'll take this as the reference height, and his reference height doesn't change. For this guy, we're taking this as the reference height, okay? So essentially, M1 G Y initial, so only this guy's potential energy is changing. So his initial potential energy shows up as the kinetic energy of both those guys, because they're both going at the same speed. Okay, did you guys understand that? All right. Find the speed of the block. So, okay. So V is 2m1 g y initial divided by m1 plus m2 square root of that. Yep.
Can you explain what their energy is equal to the additional final energy is equal
Oh, there are no non-conservative forces acting. You're not pushing on them, and there's no friction acting on them. So work done by non-conservative forces showed up as change in mechanical energy. If this guy is 0, so, okay. All right, so now let me, oops. All right, I was going to show you a second way of doing it by calculating the acceleration and then calculating the final velocity. I'm not going to do that because this next problem is long, and then I want to get started on chapter 9. Okay. All right, this problem says an object of mass 10 kg is released at point A, slides to the bottom of the 30-degree incline, then collides with a horizontal mass spring, compressing it a maximum distance of 0.75 meters. Yeah. So the spring constant is that should be Newton meters. The height of the incline is 2 meters. This surface is frictionless. So what is the work of the friction on the object while it's on the incline? Okay, so this surface has friction, and friction will do negative work, and it will remove mechanical energy. Okay, so On this surface, it has friction. This surface is frictionless. And so here, mechanical energy will be conserved. Okay. So what will happen is we'll calculate the speed here, and that kinetic energy goes and compresses the spring. That'll get converted to spring potential energy. Okay. All right, so let's see. What is the speed of the object at the bottom of the incline? So what is the speed of the object at the bottom of the incline? Okay, so we'll calculate the speed of this guy using how much the spring was compressed. Okay, so this kinetic energy gets converted to the compression. Okay. So for part A, so initial energy should equal final energy. There's no friction there. The kinetic energy got converted to the spring potential energy. Okay. So the speed V is k x squared by m square root of that. Okay, what is K? K is 500 Newton per meter. The spring is compressed 0.75 meters. The mass is 10 kgs. Okay. Okay, so at the bottom, it's going at 5.3 meters per second. Yeah. Okay, so again, how did we solve this? This was a frictionless surface. Mechanical energy is conserved. All that happened was all this kinetic energy got converted to spring potential energy. Yep.
How come K was a negative?
Oh, no, the negative sign tells you the direction of the force. In this equation, the spring constant is positive. This guy just tells you, so what that tells you is this is x equal to 0. For positive x, the force is negative. Okay? So when x is positive, the force is negative. This guy is positive. Spring constant is a positive number. Mm-hmm. When x is negative, so when x is negative, the force is positive. All right, so that's part A. The part B asks, what is the work of the friction on the object on the incline? Okay, so part B. So now we know what is the speed of this guy at the bottom, 5.3 meters per second. We know how high he was. Mass is 10 kg, 2 meters. And the angle of incline is 30 degrees. Okay. And as this object slides down this incline, there's friction. Okay. There's friction acting, and what other forces are acting? Gravity. Okay. What kind of force is gravity? Conservative. So the work done by gravity can be taken into account by I'm sorry?
Change in mechanical.
Change in what?
Mechanical.
Change in potential energy. Change in the gravitational potential energy. Okay? All right, so work done by non-conservative forces, which is the friction force, is equal to change in okay, it starts off at rest. So initial kinetic energy is 0. We'll take this as the reference level for gravitational potential energy. So it has initial potential energy, it has that, and we know the height, okay? Here, the potential energy is 0, that's the reference level, so this guy is 0, okay? And we know the final kinetic energy, okay? So the work done by friction force is equal to final kinetic energy, which we know, minus mgy, okay, y initial. So we know both of that. 1/2, no, not 1/2, m times v squared by 2 minus g1. What kind of work does friction do? Negative. So that number should come out negative, okay? Okay, so as promised, friction did negative work. This says, part C says, the spring recoils and sends the object back towards the incline. So the spring gets compressed and then it'll push it back. Since this was frictionless, how fast will it be going at the bottom? Same speed. Energy is conserved, okay? So let me change this problem slightly. So if this was a frictionless surface, this would come down, compress, go back to the same height if it was a frictionless surface. So this would be a perpetual motion machine. Okay. Now, it's going back at the same speed, but this won't rise as far because it has friction. Okay. And so actually it rises this far and then comes back, goes down slower, and eventually it'll come to rest. Okay. What happened? All this energy that it had initially was turned into heat by the friction in here. Okay. If this was not friction, if this was frictionless, it would keep going forever. Okay. The spring recoils and sends the object back upward toward the incline. What is the speed of the object when it reaches the incline, which will be the same, 5.3 meters per second? What vertical distance does it move back up the incline? Okay. Now, to calculate how far back it moves up the incline, obviously it won't move that far back up. We have to calculate mu k. See, we only have the work done by friction force. We don't have mu k. So let's calculate mu k first. Okay. So for D, and I'm skipping, well, C is, you know the answer to C. So what we'll do is, so this is 2 meters, so the hypotenuse is sine 30 is, hypotenuse is 2 over sine 30. Okay, so the work done by friction force was minus friction force times h, the distance traveled, which was mu k times mg. This was mg, this is mg cosine theta. That was, and this was, we know this work done. How much work was done by the friction force? Very good, my friend. 55.6. Okay. So mu k is 55.6 joules divided by mg times h times cosine theta. Okay. What are the units for mu k? Yeah, it's dimensionless, so all those units must cancel. M is 10 kgs, G is 9.8, H is 4 meters, cosine 30. Okay. What value can mu k take? Any positive value. Very good. You're batting 1,000, my friend. Okay. So that is 1.6, and then you can use that to calculate how far back up it goes. All right, I'll quickly calculate that. So at the bottom, you're going at 5.3 meters per second. And then friction is doing work on you. And so how high you go, this will give you gravitational potential energy. Okay, so this is E final. Okay, non-conservative work equal to E final minus E initial. I'm going to quickly do this. E final, all you have is potential energy, gravitational potential energy. Initially, you have kinetic energy. And the friction force does, so this is Y final. And this distance is Y final divided by sine 30, sine theta. Okay. So the friction force does mu k minus friction force times the distance is Y final sine theta. All right, so what are we calculating? We're calculating Y final, how far up it goes, okay? Did you guys understand this? That was the hypotenuse that we calculated, okay? So minus mu k times mg cosine theta Y final sine theta equal to mg Y final minus 1/2 mv squared, okay? I'll put in the numbers because that probably will make it easy. Okay, mu k is 0.16, m is 10, 9.8, cosine 30, y final, sine 30, 10, 9.8, y final, minus 1 half, 10, 5.3 squared. Okay, you see y final is the only unknown, and you can calculate that. Yeah.